Alright guys, we're going to move on to section 6.3, and just a fair warning, this is kind of a longer section. So this section is about binomial and geometric random variables. And depending on the time of the video, I might cut this, I might make one video for binomial and I might make another one for geometric, just depends how long it goes. So let's start with a binomial random variable. Okay, so a binomial random variable is a special case of a discrete random variable. So going back a little bit, we had that one example about APGAR scores. So if you remember that, we had APGAR scores of 0, 1, all the way up to 10. And each of those outcomes, each of those scores had an associated probability. All right, so binomials kind of work the same way. It's a special case of this. Okay, it's a special case of this. Now, if a variable is a binomial variable, then it has 4 specific conditions. All right, and the way I want you to think about this as flipping a coin. So think of this example, flipping a coin. All right, so let's define flipping a coin. Let's define success as getting ahead, and tails, and failure as getting a tail. All right, so a variable is a binomial variable if it meets these 4 very specific conditions. Okay, so let's say I flip a coin 10 times. So ask yourself, when I flip a coin, do I only have 2 options? Do I either have success or failure? Well, when I flip a coin, yes. I only can have 2 outcomes. I can have success or I can have failure. All right, so the way I remember these conditions is the acronym bi-nom-e-ol. So bi stands for 2. There's 2 outcomes, success and failure. Nom looks like num, and num means number. There are a fixed number of trials. So what I told you is that we're going to flip a coin 10 times. So there's a fixed number of trials. There's 10 flips. All right, now ask yourself, I stands for independent. Is each trial independent of one another? When I flip a coin a first time and I flip a coin a second time, do the results of the first flip influence the results of the second flip? The answer is no, they do not influence each other. So the coin flips are all independent of one another. And AL looks like all trials, all 10 flips have the same probability of success. So when I flip a coin, do my odds of getting a heads equal 1/2 every time? And yes, they do. So for a variable to be a binomial variable, it has to meet all 4 conditions. If it only meets 3 of them, then it's not a binomial. It can still be a discrete, like the APGAR score, but it's not going to be a binomial anymore. All right, now the next 2 paragraphs in here are kind of hard to read. We'll have to do some examples. Okay, so you can understand these a little bit more, so I'm just going to read it. It says the count x of successes, so if I get x number of successes in a binomial setting as a binomial random variable. The probability distribution of that random variable is called the binomial distribution with certain parameters. So like for example, when we made a normal curve, we labeled that as normal with some mean and some sigma. Okay, when I make a binomial distribution, well, it's not continuous, it's discrete. Okay, so it might look something like that. So instead of using an n to describe the distribution, we use a capital B. And when I do that, I have to give 2 parameters. I have to tell what n is, that's the fixed number of trials, and I also have to give what I call the p, and that's the probability of a success. Okay. So I have to label it with those 2 things. So when it's normal, I have to give these two things. When I label a distribution as binomial, I have to give these two things. All right. And the possible values of x are the possible number of successes. So in my case, when I flip a coin, I could get 0 heads, I could get 1 head, 2 head, and the last thing is going to be 10. Okay, it's going to stop at 10 because I'm only flipping a coin 10 times. It is possible to get 10 heads. Very unlikely, but it's possible. All right. So we talked a little bit about the notation here. You have to give the number of trials and the p-value. Okay, and actually the number of trials, if I'm flipping a coin 10 times, I could actually get as little as 0. 0 successes all the way up to 10. So there should be one more bar than n if I make a histogram of that distribution. So there should be 11 bars when I get done. All right. So let's do this exercise. All right, I'm actually going to do this exercise on another piece of paper. So we're going to take it one piece at a time. All right, so part A says determine whether or not the given random variable has a binomial distribution. So if it does, it has to be a binomial variable. It has to meet the 4 conditions. So here it says in part A, genetics says that children receive genes from each of their parents independently. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let X equal the number of children with type O blood. So if I wanted to start kind of making a probability distribution, all right, how many children could have type O blood? Well, 0 could, 1 could, 2 could, 3 could, 4 could, or 5 could. Could we have 6? No. Okay. So let's kind of go through these conditions. All right. So do we only have 2 outcomes? Well, a person can have type O blood, or a child could have type O blood. That would be considered a success. And then not having O blood would be considered a failure. So do we only have 2 outcomes? Yes. Okay. Known stands for fixed number of trials. Well, the parents have 5 trials. They have 5 children. Okay. So there are a fixed number of trials here. Okay. There's 5 trials, 5 kids. So that condition is met. All right. Is the I condition met? That means independent. All right. Is each child's blood type independent of the other child's blood type? Yes, they are. Okay. So we meet that condition. All right. And what's AL mean? All children have the same probability of type O blood. All right. It tells us in the paragraph that each child has a 1/4 chance of having type O blood. So each child has that same probability, so that condition is met. All 4 conditions are met. So this will have a binomial distribution. All right, so let's do part B. It says shuffle a deck of cards. Turn over the first 10 cards, one at a time. Let y equal the number of aces you observe. Okay, so y equals the number of aces I observe. Okay, so let's think about our conditions here. Bi, nom, e, ol. All right, so let's ask ourselves, are there only 2 outcomes? Okay, are there only 2 outcomes? I can either get an ace or not ace. So we can divide this into success and failure. So that works. Do we have some sort of fixed number of trials? Well, it tells me here that I'm going to turn over the first 10 cards. Okay. So yeah, we got a fixed number of trials. Is each card independent of the next card? Not really. If I flip the first card over and it's an ace, if I flip the first card over and it is an ace, then the chances of the next card being an ace are smaller because there's fewer of them left. All right, so like when I first draw the first card, I have a 4 out of 52 chance of getting an ace. But then if I get an ace on the first card, the chance that I draw another ace would only be 3 out of 51. Okay, so it violates the independence condition and also violates the all condition because each card, the probability of getting an ace changes based on the previous card. So it fails these two conditions. If it fails any of them, you can stop. So this is not a binomial variable. Okay, let's look at part C. All right, or question C. It says shuffle a deck of cards. Turn over the top card. Put the card back in the deck and shuffle again. Repeat this process until you get an ace. Okay. So here is W equal the number of cards required. Okay, so let's go through our settings here, or conditions. All right, so when I turn over the card, I either get an ace or I don't. Okay, so I get ace or not ace. So two outcomes is met. All right, is each time I do this independent of the next? Well, since I'm shuffling and putting the card back in the deck, each turn is independent. Okay, so that one's met. All right, and because I'm putting the card back in, every time I draw, there's 52 cards, and there's 4 aces in the deck, whether I draw one or not. Okay, so every time I'm drawing the top card, I have a 4 out of 52 shot of getting an ace. Okay, this is the hard one to think about. Is there a fixed number of trials? Okay, is there a fixed number of trials? Well, not really, because here I'm not drawing just 10 cards. All right, the number of cards required, I mean, I could do this a million times. I could shuffle a deck, draw the top card, not get an ace. Okay, it could take me a long, long time. There's no fixed number of trials. All right. That's kind of hard to see, but if you think about it, there's not a fixed number of trials. So it violates the gnome condition. Okay? So this one is not a binomial variable. The only one that is this first one of these three. All right. So now let's go ahead and read about binomial probabilities. So kind of like we did with APGAR scores, they gave us this table. But if it's a binomial variable, there's ways to calculate these numbers. Okay, there's ways to calculate these numbers. All right, what we do, the probability that I get k number of successes is the number of arrangements that I can get k successes times the probability of success raised to the number of successes. So let's kind of break it down. This P is the chance of success, and the K is the number of successes. All right. This 1 minus P, if P is the chance of success, 1 minus P would be the chance of failure. And the N minus K would be the number of failures. And then in front here, the number of arrangements of K successes. Okay, so like, if you have 4 kids, what's the chances that exactly, or how many ways can one child out of 4 have type O blood? Well, the first one could be a success, and then you could get failure, 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 and then you could have a failure, then success, then failure, failure. You could have 2 failures, a success, then failure, and then you could have 3 failures and then a success. Okay. So like in this case, we would try to be finding probability x equals 1, the probability that I get exactly 1 success, but there's 4 unique ways that I could get 1 success. So since there are 4 unique ways to get 1 success, I would put a 4 in front. Right? This is usually the hardest part to think about. That's the hardest part to think about. We can find that several different ways. And this part is called the binomial coefficient. All right, it's called the binomial coefficient. So the way we can find this thing, there's a formula to help us out. Okay, that's the formula. Okay, or we can use the appropriate row of Pascal's triangle. And it's going to be hard to understand this, but we're going to do an example here so you can a little bit more. All right, so if I just put that new notation in here, here is the formula for any binomial variable. All right. It's a really nasty formula, but the calculator is going to do it for us. But we will do one by hand. Okay. So here's the exercise. It says each child of a particular set of parents has a probability of 1/4 of having type O blood. Suppose the parents have 2 children. So let's just define a couple things. All right, we're going to let x equal the number of children who have type O blood. All right, so if I start to make a probability distribution chart, I can have 0 of my children have type O blood, I can have 1 child have type O blood, or I can have both have type O blood. All right. So it says list the sample space of all possible outcomes using letters S and F for success and failure. So for example, if I have no children with type O blood, how does that happen? That means the first child is a failure with regard to type O blood, and the second child is a failure. Okay. Now, how can I get 1 child to have type O blood? Well, the first child can have type O blood, that would be a success, and the second child would not, so that would be a failure. Or it could be reversed. Okay, the first child could fail to have O blood, and the second child could be a success. All right. Or we can have both children be successes. Okay. There's only one way to do that. They both are successes. Okay. Now, so here's what we're going to do now. So there's only 4 outcomes. Okay, there's only 4 possible outcomes. Both children do not have type O blood. 1 child has type O blood. There's 2 different ways to do that. Or both children have type O blood. There's only one way to do that. Okay. So what's the probability that neither children have type O blood? Okay. Well, how many ways can we do that? There's only one way there. So we'll start by multiplying times 1. All right. Now kind of look up here in the formula. So what this 1 is, that is this part. Okay. Now let's look at this next part. It says p to the k. What's the probability of getting type O blood? Well, it's a fourth. They told me that in the problem. How many of them had type O blood? Well, neither of them did. So that would get raised to the 0 power. If 1/4 is the probability that they have type O blood, what's the probability that they do not? What's the probability of failure? 3/4. Both of these add up to 1. Okay. So in this case, how many failures did I get? Well, I had 0 successes, so I had 2 failures. Okay. So if you multiply those things out, 1/4 to the 0 is just 1 times 1. 3/4 squared, well, 3 squared is 9, and 4 squared is 16. All right. So coming over here, all right, underneath the 0, the probability that I have 0 children with type O blood is 9/16. How do I find the probability that 1 child has type O blood? Well, first we start with the number of ways I can succeed. Okay, there's 2 different ways here that I can succeed. So I start with the number 2 times the probability of having type O blood. So the chances of success are 1/4. Now, how many successes do you have? You have 1. Now we do the probability of failure. If 1/4 is the chance of succeeding, 3/4 is the chance of failing. So we had one child that had type O blood. How many children did not? Okay. 1. Okay. So if you multiply this out, 4 times 4 is 16. 2 times 1 times 3 is 6. So the probability that one of the children have type O blood is 6/16. Okay. Now, let's do the probability that both children have type O blood. How many ways can both children have type O blood? There's only one listed way. So we're going to start with the number 1 there. Okay. All right. Then we do the probability of success, 1/4. Well, in this case, how many successes do we have? All right. Both children are successes. Then we take 3/4. How many children failed to have? 0. Okay, so 3/4 to the 0, that just becomes 1, so I don't care about that. All right, 1 times anything is itself, so let's just look at this part. 1 squared is 1, 4 squared is 16. So this number down here is 1/16. If you notice, these 3 numbers add up to 1. 9/16 plus 6/16 is 15/16 plus 1/16. Okay. Now, with bigger data sets, it becomes a lot harder to list all the outcomes. Well, what do you notice here? How many ways could 0, look at these leading coefficients, 1, 2, 1. And I said that those were the same as this part. It's the number of arrangements that are possible. Okay, well, another way to figure that out, okay, other than using the formula, is to use Pascal's triangle. Okay, so if you're going to use Pascal's triangle, all right, if we're talking about a fixed number of trials is 2, then we would use row 2 of Pascal's triangle. Okay, so if you haven't seen Pascal's triangle before, the way we make Pascal's triangle is we put 1s down the sides like this. Then it becomes pretty easy. After you make row 0 and row 1, the 2 numbers, you add those 2 numbers together to get that. So 1 plus 1 is 2. All right. And then there's nothing out here to add this 2. That's why 1 just goes down the side. Now how did I get this 3? I added 1 and 2 together. How did I get this 3? I added these 2, that 2 and that 1. Here 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Okay. But let's focus on this row. Look at this. It says 1, 2, 1. Okay. So going to this row, it says 1, 2, 1. What do you notice about these coefficients? 1, 2, 1. There's one way. What's that first way? There's one way to get 0 successes. This 2 means there's 2 ways to get 1 success. And this 1 means there's 1 way to get 2 successes. So by knowing Pascal's triangle, you can actually figure out these leading coefficients. So we put the numbers in here. Do these add up to give me 1? Yes, they do. That equals 1. So it is a valid probability distribution. All right. Let's also find the cumulative probabilities. That means the probabilities of that number and less. So we start at 0. 0 children have type O blood. There's a 9/16 chance that 0 children have type O blood. Now, what's the cumulative probability that 1 or less? Add these numbers together. Okay, so take 9/16 plus 6/16, that's 15/16. Okay, and now take 15/16 plus 1/16 and you get 16/16. Okay. So the probability that 1 or less children have type O blood is almost everybody. All right. So there's an easier way to do this. Let me show you the easier way. So in our case, let's go into our lists. So those are the number of children that could have type O blood, 0, 1, and 2. Okay, but if we go up here where it says L2, I can actually calculate the binomial probabilities. Okay, here's how we do it. All right. Actually, before we do that, if I go under my distribution menu and I scroll down till I get to letters A and B, binom PDF, binom CDF. Let's start with binom PDF. So if I click that, it's saying how many trials do I have? I have 2 trials, 2 kids. What do I put in for P? What's the probability that they have type O blood? That any one of them has type O blood? Well, that's 1/4. I can even put it in like a fraction. All right. Now they're asking me for the X value. This right here are the 3 X values. Okay, so if I type in 0 here and I paste, it's going to give me a number. Guess what? If I change that into a fraction, I get 9/16. It does everything for us. Okay. If I do the same thing but change the X value to 1, okay, and then change that number into a fraction, it's 3/8. But guess what? 3/8 is the same thing as 6/16. If I go for the last number, gives me that, and as a fraction, that's 1/16. So it will do that for me. It will tell me the binomial probabilities. All right. So let's go to the lists again. There's a way you can do this all at once. So here's how you do it all at once. List your possible X values in list 1, then toggle up to where it says L2, go under your distribution menu, go down to option A, binom PDF, click enter. Okay, so how many trials do we have? We have 2. What's the probability? It's 1/4. But I want the calculator to look at the value in list 1 as the x value. So that's the only change. I'm going to paste it there, and then I'm going to hit enter. There we go. It just gave it to me as decimals. So there's a 56.25% chance that no children would have type O blood. There's a 37.5% chance that one child would have type O blood. And there's a 6.25% chance that both children would have type O blood. Okay. So that's the individual probabilities for 0, 1, and 2. Now, in this chart, we talked about cumulative probabilities. All right, what's the chance that one or less children have type O blood? Well, there's a button for that too. Okay. Instead of using the binom PDF, if I go back under my distributions menu, there's something called binom CDF, which stands for binomial. C stands for cumulative density function. Okay. So again, we have 2 trials. The P is 1/4, and I'm still going to pull my X value from list 1. Okay. Look at this. Okay. Now you have 9/16. This number is equal to 15/16, and 16/16 is 1. So that's the difference between binom PDF and binom CDF. All right. So binom PDF is where X equals K successes. That's what it gives you. Right, these individual numbers. Binom CDF gives you X is less than or equal to K successes. So what it does is it calculates these individually and it adds them up to give you that. Okay. It also says here, using your calculator, make a histogram of the binomial distribution. Well, the binomial distribution, L1 are my X values, L2 are the probabilities of getting those X values. So if I want to make a histogram of list 1 versus L2, that's what the right histogram would be. Okay, so go back under your stat plot, all right, turn it on, make a histogram. Your X list is in L1, it's the number of kids, and your probabilities are in list 2. And then just do a zoom 9. It's probably not going to look very good. So let's change it a little bit. We went from 0 to 2 kids, so I'm going to make my X from -1 to 3, but I'm going to scale it by 1s. And I'm going to make my Y min 0, and I'm going to make my Y max 1. So when I do that, I get a decent probability distribution. If I hit trace, there's my probability distribution. So let's copy that over. All right, so if X is 0, 1, or 2, this number was 0.5625. Of course, you would want to scale it appropriately. Okay, so if I'm just looking at my histogram, it tells me there 0.5625, 0.375. Then 0.0625. We would say that this is a binomial distribution, or I could say X is a binomial distribution with a fixed number of trials of 2 and a probability of success of 1/4. So that's how I would notate it. All right, there's 2 fixed trials, 2 kids. The probability is 1/4. So we talked about these already, but the calculator commands binom PDF. It's finding a single probability of x equals k successes. CDF is x is less than or equal to k. So let's answer this question. It says, what's the probability that 1 child or less has type O blood? That means the probability is x is less than or equal to 1, because that means 1 or less. All right. So how would we do that? We would look at our cumulative probabilities of 1 or less, and there's 15/16. Or 0.9375. On our list, if we go back to our list, that's this number right here. 1 or less. 1 or less kids having type O blood, there's a 93.75% chance that that happens. So let's try this next one. So it says a local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touch screen display shows the message, press here to win a free lunch. A computer program then simulates 1 card being drawn from a standard deck. If the chosen card is a 3, then the customer's order is free. Otherwise, the customer must pay the bill. Okay? So the probability that I get a 3, how many 3s are in the deck? Well, there's 4 3s in the deck. How many cards are in the deck? There's 52. If you want to simplify that, you can, but you don't have to. It simplifies to 1/13. All right. Part A. All 12 players on the school's basketball team place individual orders at the restaurant. Okay. What is the probability that exactly 2 of them win a free lunch? Okay, so the 12, there's a fixed number of trials. Okay, 12 of them are ordering lunch. All right, and they're each going to play the game. But the first person's results doesn't impact the second person's results. So they are independent. Every person has the same probability of getting a free lunch, 1 out of 13. So all the conditions are good. Okay, all 4 conditions are good. So let's let x equal the number of players who win a free lunch. All right. So in part A, what we're trying to do, and let's define this. Since it meets all 4 of the binomial conditions, x is a binomial variable with n equals 12. There's a fixed number of 12 trials, and the probability of success is 1/13. Okay, so in part A, it's saying find the probability, so I use a capital P, that the number of players who win a free lunch are exactly 2. So we want to figure out what's the probability that x equals 2. Okay. So let me show you the formula way, and then I'll show you the easy calculator way. All right. So what we would have to do is, if we use the combinations method, we have 12 players. How many ways can we get 2 successes out of 12 players? Okay. Times, what's the probability of getting a success? 1/13. How many players got a success? 2. What's the chances of getting a failure? Well, if 1/13 is the chance of success, 12/13 is the chance of failure. And if 2 people got a free lunch, that means that 10 of the players did not get a free lunch. Okay. So if we did this by the formula, all right, I would take 12 factorial over 10 factorial times 2 factorial. Okay, so what is 12 factorial? Well, that's 12 times 11 times 10 factorial. Okay, over 10 factorial, 2 factorial. So the 10 factorials cancel there. So you're left, what's 2 factorial? That's just 2 times 1. 12 over 2 becomes 6. All right, so just this part alone, there are 66 different ways to pick 2 winners out of 12 people. There's 66 unique ways, because you're left with 6 times 11. All right. Now, what is 1/13 squared? Well, let's just do that in the calculator. So let's just kind of go from here and figure out what the number is going to be. So I have 66 times 1/13 squared times 12/13 to the 10th power. So I have 66 times 1/13 squared times 12/13 to the 10th power. All right, so if I do all that, I get this, 0.1754. That means there's a 17.54% chance that exactly 2 of them win a free lunch. Okay, so how did I get these numbers here? 12 factorial, you take the top number and write factorial. And what about these 2 numbers? You subtract these 2 from each other, so you get 10. And then you take the bottom number right there, and you put it there again. And factorial just means 10 factorial is 10 times 9 times 8 times 7 all the way down to times 1. So here I stopped at 10 factorial because there was another 10 factorial on top of it. I knew they would cancel. All right. Now, easier way to do this would just be to go to, this is an equal sign, which means I need to use binom PDF. So if I go to binom PDF in my calculator, go under my distributions menu, go down to option A, okay, there's 12 players, so there's 12 trials. The probability that any one of them wins is 4 out of 52, so I can put 4 out of 52 or 1/13. All right, the number of successes, exactly 2 win. And I paste, and I hit enter, and what do you notice? It's exactly the same number. So this distribution is just a quick way to do this. Okay, it's exactly the same number. All right, so I could have used binom PDF. The number of trials are 12. The probability of success is 1/13 or 4/52. All right, and then they're asking you how many successes. They call that the X value. How many successes? 2. All right. When you're doing this on your test, okay, or the AP test, the graders do not want to see that. They do not care about your calculator syntax. Okay. What will get you full credit? I could have actually ignored all of this stuff. Okay, and I could have ignored this. I could have simply written the answer down, but I would have to tell the reader that I know it's a binomial distribution. Okay, I would have to define my variable. That, you would need that part. Okay, so I would need this, I would need this, I would need this, and I would need this. And it would also be good to discuss why it's binomial. So check the conditions in words. All right. Now, part B. It says if 250 customers place lunch orders. So here the number of trials just got changed. Okay, there's 250 now. It says, what's the probability that fewer than 10 win a free lunch? So now I want to figure out, still the probability of success is the same. It's 4 out of 52, or you could write that as 1/13. All right. But now they want to know what's the probability that less than 10. That's what less than 10 means, less than. Well, what does it mean to be less than 10? Remember, x are the number of people. You can't have a decimal number of people. So the probability that x is less than 10 means the same thing as the probability of x is less than or equal to 9. I need the bar underneath here to use binom CDF. So now I can actually use binom CDF, which means cumulative. All right, so if I go under my distributions menu to binom CDF, which is cumulative, I have 250 trials. The chance that I'm going to win is 4 out of 52, and I want to put 9 in as my value because, again, it's cumulative. 0.00613. Okay, so there's like 0.6% chance that less than 9 people win. Okay, so what the calculator is doing, it's adding up. Let me show you up here. What the calculator is doing, it's adding up the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 all the way up until we get to the probability that x equals 9. That's the last number that matters because we want the probability that 9 or less. So it's basically doing this type of calculation 10 times from 0 to 9. That's what it's doing. So we'll do one more example and then I'm going to cut the video and make another one here because this is going kind of long. So this exercise, to introduce your class to binomial distributions, Ms. Desai gives a 10-item, so there's a fixed number of questions, multiple choice quiz. The catch is students must simply guess an answer, A through E. So there's 5 answer choices. So the probability, if you're just guessing that you get it right, would be 1/5. So P equals 1/5, and the number of questions on the test are 10. All right. Mrs. Desai uses her computer random number generator to produce the answer key so that each possible answer has an equal chance to be chosen. Patty is one of the students in the class. Let X equal the number of Patty's correct guesses. Remember, she's just guessing. So part A, show that X is a binomial variable. All right. So to be a binomial variable, it has to meet the 4 conditions. So we can guess correctly. That would be a success. Or we could guess incorrectly. And that would be a failure. Known, fixed number of trials. There's 10 questions. Okay, each question's guess is independent of the next question's guess. Okay. And AL, all questions have probability 1/5 of being guessed correctly. So part B. It says find the probability that x equals 3. Okay. So this is a binomial distribution. All right. So here we can say x is a binomial distribution with fixed number of trials equals 10, and the probability of success on any trial is 1/5. Okay. So this is equals, which means I'm going to use binom PDF. So if I go back under my distributions, I'm going to use binom PDF. There's 10 trials. The chance I get any question right is 1/5. And I want to figure out what 3 is. What's the probability that I get exactly 3 right? Okay, 0.2013. There is a 20.13% chance that Patty guesses exactly 3 questions correctly. All right. So, part C. To get a passing score on a quiz, a student must guess correctly at least 6 times. Would you be surprised if Patty earned a passing score? So we have to figure out what's the probability of getting a passing score. So the probability of getting a passing score is the same as the probability of getting 6 or more questions right. So what we're trying to do is we're trying to find the probability that x is greater than or equal to 6. Well, there's no button in our calculator that does that, a greater than. Okay, so if I thought about this in terms of just a discrete random variable, all right, so if I had my numbers, if I have 10 questions, I could get 0 right, 1 right, 2 right, 3 right, 4 right, 5 right, 6 right, 7 right, 8 right, 9 right, and 10 right. So I want to figure out what's the probability that I get 6 or more right. So what I would be doing is I would be adding up those individual probabilities between 6 and 10. An easier way to figure that out is you know that this circled part and this circled part together have to add up to 1. Okay, so this red part, the sum of all those reds and the sum of all these blues have to add up to 1. So to find this blue part, I can just do 1 minus the probability of the red part. And what's this red part? It's the probability that x is less than or equal to 5. I can do this in the calculator. Okay. Because this is a less than or equal to, I can use a binom CDF to figure out what that part is. Okay. So if I start to do this in the calculator, I can do 1 minus binom CDF, because it's a cumulative. Okay, again, there's 10 trials. Chance of getting any question right is 1/5, and I want this x value to be 5. Okay, so it says same thing, 1 minus this thing, which is a binom CDF. And my final answer here equals 0.00637. So what does that mean? This isn't even a percent. All right, so this is like saying 0.637%. There's less than 1% chance that Patty would get, or any student would get, a passing score. All right. What do you think? Would you be surprised if someone earned a passing score if they only have that type of chance to get a passing score? Yes, you'd be very surprised. I would be very surprised if Patty earned a passing score. since there is less than a 1% chance of doing so. And this number is less than 1%. All right. So that is how you do binomial distributions and calculations. That's how you do them. All right, I'm going to stop the video here, and we're going to pick up the next video on how to easily calculate the mean and standard deviation of a binomial distribution. So that'll be the next part of the video.